out not to have any dynamical significance when you put it in. I think you can describe, well, the trace, you can include it, but you can also eliminate it from the theory, basically, by subtracting out. It's an overall scalar in the space, so if you want it, you can have it, but you're not required. So I suppose somebody else. Well, they happen via the gluon. So the theory is there is some they're exchanging gluons, and the idea is it's such a powerful, analogous to the way that nuclei and electrons exchange photons, sticking them together. The gluons do this by some not fully understood mechanism. I mean, gluon exchange is not enough. This is the problem of quark confinement. So what people did phenomenologically is say, okay, we don't exactly know the details of how quarks are confined, but they appear to be confined. So what are all the possible condensates we could make out of a quark-anti-quark pair? So if you like, these are all possible meson states you could make out of n distinct equations in left and right sections. And then you leave. So the idea was, let's not worry about how this works. Let's just say that it works, and what would be a good Lagrangian for describing quark and quark boundaries. That's the philosophy. I probably should have said that. To the best of my knowledge, I would say, strictly speaking, quark confinement is still an unsolved problem. We have hints that it ought to work, but I don't know of anything that actually definitively proved it. There was a lot of effort given to it, and then sort of decided to do other things. So the issue, what I wanted to do on this is just mention where the anomaly comes into this thing. So this is not everything. It still needs the anomaly. And the reason is that if you did a path integral over the action associated with that L and worked out what the effective action was of the gauge field, you would find that it would have this kind of structure that I mentioned last time, that XA acting on this effective action would equal GA acting on the gauge field, and if this is not the variation of some local functional, then we have an anomaly. Because if it were, you can show, if this were an equality, you could basically show that this could be reabsorbed into that using counter terms. But if it's not equal to a variation, then it cannot. Sorry? It's hypothesized as the action that, where'd it go? It's hypothesized to be the action that associated with these condensates that obeys the criteria that you have the smallest number of derivatives so that you've got the proper low energy physics, and that it respects, it's invariant when you do this. So that's why you need the trace. You've got a B left right dagger, B left dagger, and the trace cycles it out. So this was a hypothesis. This is the proposed low energy effective action for the condensate. It's not something that is, how shall I say it? It's not something that was mathematically derived from the original action in a direct sense. Rather, it came from the expectation that the interaction of what goes on here generates this via some physics we don't entirely understand, but we'll say once we've got this, what is the right way to describe the physics of this structure here? And so they say, well, the simplest thing we can write down is that this is just the derivative of the I mean, if you look at the definition, this is just the derivative of the condensate times the derivative of the dagger of the condensate. That's all it is. So the idea is the condensate is the kinetic energy of the condensate. So how do these condensates interact with each other? Well, to leading order, we're not going to put in interactions until we understand the leading order, so you can do that. But one of the interactions that has happened comes from this. Then you might imagine you want to put others into the theory. But it turned out this was remarkably, forgetting about the anomaly, this was remarkably effective for describing kaons, pions, eta mesons, rho mesons, all of these different mesons, and their varying decays were very well described by this simple thing. But there were a few things that did not work. One was pi and photons, which was why they used this. So that's where that came from. It's not a renormalizable Lagrangian. But that doesn't matter because the idea is it's a low energy effective Lagrangian. So when you go to high energies, the condensate dissolves and the actual thing. I'll write it over here. It's hard to see, sorry. Pi is defined as 1 over twice f pi times this condensate dotted into the gauge field generator. That's all that pi is. It's a common notation, yeah. Well, it is. I mean, we did that. If you look at what the pions do, in some sense, that's what we did whenever it was Monday of this week, I think, or Tuesday, I forget. But so it is. But the point is to generate this without worrying about those triangles. See, the quarks have all disappeared at this formulation. The mesons are all either pseudo-scalar fields or pseudo-vector fields or something like that. So the idea is, can you describe those interactions without going back down to the quark level? And the answer is, yeah, that term doesn't. That's the point. So you could. In fact, that's what people did. And so that's the connection. Does that make sense? Basically, yes, that's right. At the condensate level, that's correct. The idea is the quark terms just get wiped out entirely. The mesons have no idea they're made of quarks. They behave according to that effective action with that other term. And this works very well, actually, to describe low energy meson physics. In fact, it works better, I think, than people thought it ought to work when they constructed it. So the idea of that was to show you, it was to follow up on what that X gamma stuff does. It's used in generating it can be used in generating effective actions, and partly, I guess, still is used if you're a person who believes that there is substructure to quarks or leptons or what have you, then similar ideas would be used, that an electron is the condensate of, I don't know what, preons or regions or something. Those ideas were used there as well. To my knowledge, there is no positive evidence to support these kinds of substructure models, and people don't work on them anymore, or hardly anybody works on them anymore for that reason. And the favored substructure model, if you can call that, would be something like string at this point in history. Yeah. Pardon me? I don't know why you use the word maybe gray magic. What do you mean? I mean, yeah. In some sense, yeah. For the abelian anomaly, it can't. There are theorems that show that you won't affect it. As I said, for the non-abelian anomaly, everybody thinks the same is true, but I don't know that there's a genuine, rock-solid proof of that. What happens if you add any other terms? You can add other terms to that thing. But remember, the condensate, there's a dimensionality to the condensates, which is expressed by that f pi squared, right? Q bar Q is not a unitless quantity. It has dimensions. That's what the function of the f pi is. So anything else you add, so the argument goes, would be that is a function of the condensates, would be dimensional, and it'll be suppressed by powers of a mass breaking scale. So you can do it, but unless that mass scale is very low energy, those other terms won't matter very much. But this one does matter, comparable to the other one. In some sense, compared to that term, this is the most important. And the hypothesis here is simply it's the kinetic energy of the condensate. What's the simplest thing any physical structure can do? Well, it has energy of motion, right? Which is basically what that is. Relativism. So, all right. So what I think I'll spend the rest of the time on, I won't get through all this, is this notion of an index theorem. So, just to give you some introduction to some of the mathematics behind this. There was this notion that d star of J5, remember, we saw in the path interval derivation, was twice the sum of phi n dagger gamma 5 phi n